Hi everyone, my name is Jiayang, a first-year PhD student at University of Alberta. Today I'm going to introduce our paper, When Cyber-Physical Systems Meets AI, a benchmark, an evaluation, and a way forward. When people talking about cyber-physical systems, they refer to the type of systems that combines the physical plant with computer units. And the computer units can help to monitor and control the output behavior of the mechanical components based on the environment information collected by the distributed sensors. So nowadays, CPS has been developed widely in different industrial domains such as energy system, aerospace, and medical devices. So considering the integrated characteristic of CPS, it can combine the mechanical part and the computer part, cyber. So it has been considered the key element in the new upcoming industrial revolution, Industry 4.0. This new revolution mainly focused on the internal connectivity, automation, machine learning, and real-time data. So regarding the machine learning, with recent advances in artificial intelligence community, AI has been considered as a great complement to the existing CPS because of the great learning and generalization capabilities of deep neural network. AI can be developed on the CPS for perception, prediction, and control. So we call these types of new CPS systems merged with AI components as AI-enabled CPS. In traditional CPS, the control tasks are accomplished by some classical controllers, such as mode predictive control, PID control, or linear quadratic regulator. For CPS with AI controllers, the control objective can be done by different AI-based methods, such as supervised learning or reinforcement learning. Among all these different AI methods, deep reinforcement learning is considered state-of-the-art, and it has been proved and succeed in various application domains. So because of that, for this study, we mainly focus on the DRL-based controllers on AI-enabled CPS. Although AI-enabled CPS shows the promising potential, both industry and academia are seeking to advance and explore further on this path. Unfortunately, there is a lack of deep understanding about their characteristics, such as the reliability, efficiency, sustainability, and security. We cannot directly deploy these techniques on practical applications without comprehensive understandings. So one of the reasons for this critical situation is that the researchers do not have great platform to study and analyze the AI-enabled CPS. Unlike the large and growing open source community in conventional software engineers, CPS are often kept as private intellectual properties by some companies. So there are only few benchmarks and public datasets available. To bridge this gap, we take the first step of benchmarking AI CPS in different industrial domains. And for this study specifically, we also make a systematic analysis on the performance of AI CPS in contrast to the traditional CPS. So here is the research workflow of our study. First, we collect CPS with 3 specific selection criteria from different industrial domains. And then we construct AI CPS based on state-of-the-art deep reinforcement learning techniques. And we also compare the performance of AI CPS with traditional CPS from the essential property analysis and falsification. For the falsification is used for in-depth evaluation. And in the end, we make an early investigation on the hybrid control systems. We combine the traditional and AI controllers to see if they can achieve better performance together. And detailed information about each section will be introduced in the following slides. For the benchmark collections, we consider the candidate CPS must be open sourced, and we can modify the system to replace the traditional controllers with AI ones. And the system should come with comprehensive documentations such that we can configure the system environment properly. Also, as we use deep reinforcement learning-based controllers, we need to understand the system requirements to design a good reward function. Also, the selected CPS must reflect the industrial level complexity in order to get useful insights and implications from our experiments. We use Simulink as our modeling platform since Simulink has been widely used in industry, and a consistent platform makes it easier to set up and run our benchmarks. In general, we collected 9 subject industrial level CPS in 7 domains, such as power grid and wind turbines. Each system comes with a built-in traditional controllers like mode predictive control, PID control, and lookup table. And we also use the number of blocks inside the Simulink mode to measure the complexity of the system. As I mentioned, we design multiple AI controllers for each system as we want to get a comprehensive understanding of the capability of AIs. We experiment with different types of learning algorithms, different agent configurations, and diverse reward function settings to explore the capability of deep reinforcement learning controllers. Among all these variants, we select the best controllers with competitive performance for later comparison and analysis. To test and evaluate the performance of AI CPS we constructed, besides trace analysis, we apply falsification, which is a commonly used technique to detect defects in traditional CPS. Also, we use signal temporal logic, STL, a widely adopted specification language to describe the system requirements from the documentations. Since we collect CPS from different domains, they have different operation requirements. We want to have some consistent tools to analysis and evaluate the performance. Basically, falsification formulates the testing problem as the optimization one by taking the robustness as the objective function. To solve the optimization problem, falsification uses hill climbing algorithms to detect the defects. Then we move to the comparison and evaluation part. We also propose 3 research questions. The first one is about the performance of AI CPS and traditional CPS. It aims to compare 2 kinds of controllers to understand their strengths and weaknesses. We simulate each system with different controllers to collect and analyze their output traces. We also propose a series of metrics to describe their behavior comprehensively. We use 5 different metrics to fully describe and understand the system's behavior during the simulations. The first metric is called hard safety. It represents the safety requirements that should be strictly satisfied during the entire simulation. The second one is soft safety. It measures the average and maximum error from the reference values. And followed with the steady state. This metric tells us how stable the system is. And the resilience, the fourth one, aims to observe the system's ability to recover from some fluctuations. And the last one is liveness. This one is applied just in case a controller makes some conservative decisions to passively meet the control requirements. So here is the experimental results of our first research questions. These 9 radar charts shows the performance of controllers with respect to the 5 evaluation metrics we proposed. For the hard safety metric, AI controllers have similar performance with the traditional ones in 6 systems we highlighted here. So it indicates that for safety metric with random sampled input, it's hard to distinguish and compare their performance. We need some in-depth and advanced testing techniques, such as falsification. For soft safety metric, the traditional controllers have good performance in 5 systems. Compared with the results on the first metric, there are fewer traditional controllers that outperform the AI controllers on soft safety metric. And we also noticed that some of the signal outputs from traditional controllers are unstable compared with the AI ones. On the side of the AI controllers, it has good results on 7 systems, and based on this, we can conclude that if a system have too many performance requirements or multiple control outputs, a standalone DRL controller may not handle these situations as good as the traditional one. For the steady state metric, most traditional controllers can provide a decent stable outputs, only except 2 systems like SC and WTK. The poor performance of these 2 systems can be considered as their unstable outputs from the PID controllers. In contrast, DRL controllers show good results in all these systems. And we also find that with different configurations, DRL controllers on same system may have a variance in their performance. Then we move to the resilience metric. Both DRL controllers and the traditional controllers show good results on 5 systems, since this resilience metric is only applicable on 5 target systems. We also find that for some reinforcement learning controllers, they may perform well in this resilience metric, but they fell short in the first and second safety metrics. So based on this consideration, this type of DRL controllers cannot be considered as reliable systems. For the last one, liveness metric, all of our controllers, no matter the traditional ones or the AI ones, they have good results. It's a good news since none of our controllers are passively satisfy the safety requirements. So combine the findings from the following metrics, we find that for most systems, AI controllers have better or equal performance with the traditional ones, but they may feel struggle in several complex scenarios. So traditional controllers can be considered as a safe choice in some complicated scenarios which involve some multiple control requirements. And we observe that many controllers have similar performance, so falsification is needed to give us an in-depth evaluation. So falsification, our second research question, we want to verify the effectiveness of existing falsification techniques on AI-enabled CPS. We applied different falsification methods on each system. So on the one hand, we can get in-depth analysis of the robustness of these controllers. On the other hand, we can check the effectiveness of the falsification technique methods. The falsification tools we used are Breach and Stereo. These two are widely used with several different backend optimization solvers. So with these rich options, we can enhance the performance of defect detection. We use falsification rate as a metric to evaluate the robustness of each system. So the lower the falsification rate is, the more robust the system will be. So here are the experimental results for our second research question. We call a system falsifiable if it can be falsified by at least one falsification algorithm. So on the left graph, we saw that Stereo cannot falsify 2 systems in AFC, but these 2 can be falsified by Breach. And combining the graph on the right side, Breach solver cannot falsify 1 mode in AFC and 1 in ACC, but these 2 can be falsified by Stereo. So we notice that for any falsification algorithm, there always exists a falsifiable benchmark that cannot be falsified by this algorithm. So none of the falsification methods can dominate all the systems we have. This result proves the famous no free lunch theorem in optimization area. And it also motivates us to develop more effective algorithms to handle AI-enabled systems specifically. In the last research question, we take an early investigation on controller hybridization. We combine the traditional and the AI controllers to see if the hybrid controller can achieve better performance. We propose 3 approaches for such combination, so namely random-based, average-based, and scenario-dependent based. For the random-based, as it said, we choose the signal randomly from two controllers. And for the average method, we take the average value of two controllers as the final control output. And for the last one, scenario dependent, the control authorities dynamically switch between the controllers depending on the system environment. So here is the experimental result for the last research question. For ACC system, the hybrid controllers performs better in falsifications, like all these hybrid controllers have relatively lower falsification rate. And the scenario-dependent approach outperforms other methods regarding the soft safety metric. In the AFC system, 3 out of the 4 hybrid controllers have similar or beyond performance than the traditional controllers and standalone AI controllers. Specifically, average-based and scenario-based approaches have never been falsified by any falsification methods. We can conclude that hybrid controllers can take advantages and outperform their constituent controllers, and the scenario-dependent approaches have better results than other two in most cases. Controller hybridization is a promising direction to improve the quality of AI CPS. So we highlight some key findings from our work. First is the DRL controllers may have shortages to balance multiple control outputs based on our experimental results. And existing falsification algorithms may not work effectively for AI-enabled CPS. And the controller hybridization is possible to improve the safety and performance of the traditional CPS system. Based on the insights from our evaluation, we propose the following 3 future directions. First, we encourage more research efforts on benchmarks and empirical studies to enrich the AI CPS community. And more advanced testing techniques are required for AI CPS specifically. Besides the testing, analysis techniques should be also developed to understand the root cause of the violations. To achieve this, more research efforts on fault localization and repair are necessary. Here is a short summary of our work. We create the first public dataset and benchmark of AI CPS over different industrial domains. We also perform a systematic analysis of the performance on AI CPS and benchmark the current falsification techniques. Based on the analysis and evaluation results, we further propose some discussions on the future directions for AI CPS community. This research was supported by funding from Canada First Research Excellence Fund as part of the University of Alberta's Future Energy Systems Research Initiative. Feel free to contact us if you have further questions or need more information about our work. Our benchmark, experiment scripts, and complete evaluation results are available on our website. Thank you for listening, and goodbye.